This is section 9.6, motion along a curve. Students will find the velocity, acceleration, and speed of a moving particle, particularly using vector notation. So how do vectors model moving objects? And that's what we'll look at today. Position, velocity, acceleration, and speed. These are going to feel very familiar to the way that they did when we were dealing with functions, and especially those quadratic functions, the parabolas. Position, velocity, acceleration, and speed of a particle whose motion is along a smooth curve traced by the twice differentiable vector function. Twice differentiable just means that the first and second derivative both exist, are defined as below. So position is what's given to you, just like we had earlier. Velocity will be the first derivative. Acceleration is the second derivative. And speed, we actually just used that in the arc length formula, is going to be the derivative of the x term squared plus the derivative of the y term squared, and we'll take the square root of each. So let's look at example number 1. Find the velocity, acceleration, and speed of a particle that is moving along the plane curve from t equals 0 to t equals 2. So let's start with position. And that's what's already given to us. And again, if you want to break it apart with your x component and your y component, that might be a little bit easier. So your velocity vector is going to be the first derivative. So the first derivative of the first term is t plus 1. First derivative of the second term is 3t squared. Okay. And for acceleration, we're going to find the derivative again. So we have 1 and 6t. It is that easy. Isn't that cool? And then what we need to do is find the speed. So the speed, this is an absolute value per se, but it's notation that indicates speed around that velocity. So it's the first derivative inside of this speed formula. So the first derivative squared, we had t plus 1. For the x component, and for the y component, we had 3t squared. We'll square that again. So this is t squared plus 2t plus 1 plus 9t to the 4th. And if we just put this in order by the exponents, I've got 9t to the 4th plus t squared plus 2t plus 1. Now, give me one moment here. Answers. Our domain was between 0 and 2, but it didn't say to find, it didn't indicate to find the velocity at a particular value or the acceleration at a particular time or the speed at a particular time. So we can leave all of our answers in terms of t. Had it said find all the above when t is equal to 1, you would replace t with 1 in all of those expressions, and then you would get actual numbers. It's not bad, right? Example 2, the position of a particle of mass moving along an ellipse with an angular speed w is given by the vector function. R of t is equal to a cosine wt, b sine of wt. This is defined between 0 and 2 pi. Find the force F acting on the particle at any time t. So down here, this is what we're actually trying to prove. Now, a piece of information is missing here, and if you're not familiar with physics, you're going to have an issue with it. But that is Newton's law of motion, second law, I think. Force equals mass times acceleration. So in order to figure out what that force is equal to, m is going to be mass, we need acceleration. Acceleration comes from velocity, velocity comes from position. So if we have r of t is equal to a cosine and b sine, we want to find the first derivative. So my velocity is going to be a, that w, there's a negative in the front, sine wt, there's a chain rule in there. Same thing with the y component. Okay. Now from here, we need accelerations. We'll find the derivative again. All right, excellent. Things are looking good. If I look in here, I actually have something very much related to what we had initially. And that is A cosine, B sine. Here's my A cosine. Here's my B. Oop, I didn't take the derivative. Sine. All right, let's try again. So A cosine, B sine. So if I take those two pieces out to the end, that's actually the original position vector. So what I can do is replace that with just my R of t. And I know that feels a little weird. But anything that's underlined here in this lighter purple color, there's my RT. That's my vector. What do I have left? Well, I have a negative sign and I have a W squared with both of those. Okay, excellent. Now that's the acceleration piece. If force equals mass times acceleration, there's my force, mass times my acceleration vector. I'm going to move the negative to the front. RT, there we go. So we have proven, or we have shown that this is true. Now, you could pick a time t, you could pick an angle in there, and you would have your answer. And just because it's a Monday, when I was calling this a W, you can continue to call it a W in my class, that's totally fine. But this is really omega. And it looks different than this omega because the one below is the capital version and the one up above is the Greek lowercase for omega. So that W is really omega. Let me know if you have questions.